To the naked eye, a piece of copper is a solid, inert block, but at the microscopic scale, it contains a dense population of conduction electrons moving through the metal lattice. Early attempts to model this behavior relied on classical mechanics. The Drude model treated these electrons like a classical gas, a collection of particles bouncing randomly off positive ions. This graph allows us to track the predicted electronic heat capacity as temperature increases. Under classical Maxwell-Boltzmann statistics, every electron should absorb thermal energy. The resulting prediction is this flat horizontal line, representing a large heat capacity that does not change with temperature. Experimental data revealed a different reality. The actual heat capacity is orders of magnitude smaller and follows a slight linear slope. The classical prediction failed to match the physical evidence. Classical physics does not account for the internal mechanics of electrons in solid metals. Physicist Arnold Sommerfeld proposed a solution to this discrepancy. He retained the idea of mobile electrons, but replaced classical statistics with quantum mechanics. In Sommerfeld's model, electrons are treated as fermions. Unlike the particles in a classical gas, fermions follow the laws of quantum probability. This shift requires the application of the Pauli exclusion principle. This principle dictates that no two electrons with identical spin can occupy the same quantum state. This single quantum restriction changes how electrons occupy space and energy within the metal. We begin by modeling the metal as a three-dimensional box with a fixed volume. The electrons move freely within. We describe them as quantum waves. By applying periodic boundary conditions, we restrict allowed momentum, transitioning our analysis into wave vector space. This is K-space. In this coordinate system, a point represents a specific momentum, not a physical location. The quantum states are these discrete points. Because the metal has finite dimensions, the electrons are restricted to these specific, countable coordinates. Confining the electrons to a macroscopic box forces their quantum states into a rigid grid in K-space. At absolute zero, the system reaches its lowest energy configuration. While a classical gas would see all particles collapse to zero energy, the Pauli exclusion principle prevents this. The first two electrons, one spin up and one spin down, occupy the lowest energy state at the center of K-space. As more electrons are added, each pair fills the next lowest available energy state, stacking radially outward from the center, one layer at a time. This resulting volume of occupied quantum states is the Fermi sphere. Its radius is the Fermi wave vector, K sub f. This creates a paradox. Even at absolute zero, electrons do not settle into a state of rest. They're forced into a high-energy architecture of motion. The dimensions of the Fermi sphere are determined by the density of conduction electrons in the metal. This derivation shows the relationship between electron density and the Fermi wave vector. By counting the states within the sphere, we can isolate K sub f based on the number of electrons per unit volume. The electrons located at the very surface of the sphere represent the maximum energy level in the system, known as the Fermi energy. These equations define the Fermi energy as a function of the electron density. This chart highlights the scale of these energies. In a common metal like copper, the Fermi energy is approximately 7.1 electron volts. Compare that to the ambient thermal energy of a room at 300 Kelvin, roughly 0.026 electron volts. The electrons at the Fermi surface carry an intrinsic kinetic energy hundreds of times greater than the heat energy of their environment. How does the introduction of room temperature heat affect this architecture? This graph shows the Fermi-Dirac distribution, plotting the probability a quantum state is occupied against its energy. At absolute zero, the probability remains at 100% until the Fermi energy, where it makes a sharp vertical drop to zero. Every state below the Fermi energy is occupied. Every state above is vacant. Increasing temperature to 300 Kelvin smears that sharp boundary into a gentle curve centered around the Fermi energy. The width of this transition represents the available thermal energy. An electron can only absorb heat if it can move into a vacant state at a slightly higher energy. Electrons deep within the distribution cannot absorb thermal energy because all neighboring states are occupied. The Pauli exclusion principle blocks their transition. We can map this thermal distribution back onto our 3D model. When heated, only a razor-thin outer layer of the Fermi sphere becomes active. The massive interior remains inert. This cross-section shows the vast majority of electrons are locked in place. Only those inhabiting the glowing surface can access the empty states outside the sphere. Calculating this ratio shows that this active shell represents less than 1% of the total conduction electrons. This provides the physical explanation for the heat capacity anomaly. This equation shows that the heat capacity is proportional to the ratio of temperature to the Fermi temperature, resulting in the small, linear values observed in reality. This same small fraction of high-velocity electrons at the surface is responsible for both electrical current and heat transport, providing a theoretical basis for the Wiedemann-Franz law. The model is not a complete theory. It ignores the periodic potential of the atomic lattice, which is necessary to explain semiconductors and insulators. By treating electrons as a degenerate quantum gas, Sommerfeld did not simply correct a statistical error. He identified the high-energy quantum mechanical architecture that exists inside every metal.